Thanks. Well, but basically you have said it all, so I could stop from now. But I will show you some extra slides to highlight what has just been said. So I would like to start with what is SDC Verifier, what is the program structure, and then I will show an example of the calculation if I am on time finishing all my sheets. So typical types of structures. We have offshore units, civil engineering, aerospace, kind of typical equipment where you need specific standards. You have more and more specific standard for certain type of equipment where you need to follow these rules. Same thing for things like cranes. So how does it work? SDC Verifier is an add-on. It works directly within your Simcenter 3D software. So you don't have to exchange or re-import results. It directly works in the same environment, and you can choose either as a separate, as an embedded, as a separate GUI next to Simcenter or VMAP, or work embedded directly in a single screen. This is the total structure of the software. So at first we have your general FEA model. Then we have a tool to make a lot of load combinations possible. We have seen several other presentations in the last 2 days on specifically this topic, how to make a lot of load combinations and how to figure out what is the maximum, these kind of things. Recognition, we need to get from an elements to the structural items where we need to check on. We have the checks and the reporting part, and I will go through all this one by one. The first thing is, if you want to calculate according to rules and standards, typically you need a lot of load combinations. So that is the first thing we do in SDC Verifier. So how does that look? We have a matrix-like functionality which you can copy directly from Excel if you need, where you can set for each separate load influence, you can set a partial load factor, and then the load set combination is 1 times gravity and 1.3 times tip load in that situation. So if you see here, these are, some industries call these base cases. Then you can make your load sets, which are based on linear combinations. And then in the end, if you have a lot of load combinations, let's say if you have 30 load cases, then already it is hard to figure out, okay, what is my maximum stress or maximum buckling risk or whatever. So we created what we call a load group, which is kind of envelope where you can check all these things all together all at once. Besides that, we have some extra tools, because if you have not 30 but 3000 load cases, you would like to see, okay, which load cases are actually important. Because if I look at the maximum stress or maximum buckling risk, I also want to know, how do I improve? So we have tools like which load case gives me or gives the worst stress location on which element, so you can see, you can get an overview, okay, what are the load cases which are determining where. We call that governing tool. The other subject is, you can do that for individual loads or for load sets, but you can also make groups of results and check, okay, what situation or a position or a wave direction is the highest, has the highest influence on your criteria, which can be buckling, maximum stress, maximum tension stress, whatever you want. For example, here you can see in this example that we set for position P1, 2, 3, 4 and 5, what are the worst load cases. You can see, okay, for large parts of this example, it is either P1, which is the inward position, or P5, which is the outward position, and the intermediate load cases almost do not appear, unless only for this boom situation here, where actually a position slightly smaller was important. So you can get a quicker overview with these tools. Okay, what is really important, and if I want to make updates or improvements to my design, where do I need to look at first? We have some specific tools which are nice for especially if you have to deal with wind or waves or things like that. We have tank loads where you can set for each tank. You only have to set the tank content, so the amount of volume or the total weight, and the water level is calculated automatically. Wind load according to standards, wave loads according where you just apply a pattern and you make a selection of all the elements you want to apply the load to, and that is done in a couple of seconds. So that is the load combination first check. Then we go to the recognition part, which is absolutely necessary in order to make code checks available. So we recognize any XYZ structure in a model. So for a ship, that is frames, decks, and longitudinals. That's very nice also for reporting, for example. And then we have the structural items which we recognize, which are joints, beam members, all welds, including crossing welds, weld tips. So some extra information is freely available, and also stiffeners and plate fields for the plate buckling checks. These are the implemented standards. We have some more. You can build your own standards. But what is nice to know is that everything is completely open. So you can see actually what are the rules which are implied. And if you have a discussion with, for example, Lloyd's, and you want to use DNV rules, they might say, okay, that's all fine, but then you need to change formula 3.45 and change this factor to 0.3 in 0.45. That's no problem. You can adapt that, re-password protect that, and divide between your colleagues at your company. The last part is the reporting part. If you have a lot of load cases, you want also to have very extensive reporting capabilities, because sometimes it's required to have all your load cases, even if you do not check them one by one, to have them reported. That can be an issue. Another issue is that you want to communicate with some other people, where you want to say, okay, for the CAT guys, check if all the components, all the weights are still the same, these kind of things, and or get an overview where you get pictures for different sites, where people can say, okay, can I change, can I add holes or stuff without re-asking the FEA guy if the strength is really okay. So what is nice to know, we have a general setup, standard setup file. So the complete description of your full model, including all the weights, which elements do you use, which properties are defined but do not have any elements. So this is great to find out small or bigger errors in your model. We have the results per load set, where you can set up once. It's a really quick method. You set up, okay, for one load set, I have, of course, a description, what is my load. I have reaction forces, some of the maximum displacement table, and a plot, stress plot, maximum stress table, whatever you want to add. If you're done and you're happy with that, you can copy that to all other individual loads, load sets, and load groups. So this is extremely fast to get a useful document. And what is also nice is that everything is bookmarked, both in Word and in PDF, so you can quickly go to the section which of your interest. So if somebody asks, okay, yeah, but I don't think that load case 7 is really an important one, you can go discuss directly that situation. So you make this report a digital one. I would advise you not to print it. These things can be up to 1,000 pages easily. But you have a document which is used with these bookmarks to quickly go to the section you want. So that is, in short, the full process. And the nice thing is, if you have done all this, and there are things, of course, in the design phase not everything is directly okay immediately. So if you update your model, we can do this full calculation again by clicking on, okay, can I get the new reporting tool, and then say, hey, there's no results. Do you want to calculate as well? And the full process is only calculation time, computer time, and not human effort time. Yeah. So this is a big time saver. Okay. I will go quickly to a couple of examples. You can do, for example, with recognition, a very important thing is that you recognize welds, because there's a difference in fatigue resistance between non-welds and welds, and you can see clearly here how that looks. I have here an example of the fat classes at the weld itself. So it's not only welds and non-welds, but it is also, if I have stresses along the weld, the resistance, fatigue resistance is much higher than if I have a stress perpendicular to my weld. So you can take that into account as well, and then you get really realistic pictures like these, where you have at ending of stiffeners, you have overshoot in fatigue resistance, while everything else, so the non-welded is almost fine. Everything is fine. And this works not only on plates, you can also do this on beams or volumes, whatever you want. Another thing is, since we recognize all these welds, you can do weld strength checks. And you might ask, okay, we do FEA analysis, so it is already there. Unfortunately not, because for weld strength it is allowed that you can have small plasticity at, for example, at the tips. What you need to do is you need to compare the total weld capacity and compare that with the total load over the weld in any direction. So what we do is, for this weld, we sum up for all the elements what are the typically loads, and then sum that all up in the global coordinate system, and then we change that into the weld coordinate system, because there you can see, there you can compare directly if your weld capacity or weld resistance is comparable to what is the real value. And then instead of having stresses and stress overshoots at the tips, you only have a single result. The weld either is okay or it's not. So you can see here, per weld I have a single value. Plate buckling, well, it works exactly the same. You can see here the labeling of the length and width of each panel, and here you have buckling results. In this case, I think it's ABS. Yeah, it's ABS buckling results, and you can of course get also all kinds of tables. And what is nice to see is that you're not bound to any mesh requirements. If you have some other code checking programs where you say, okay, a plate needs to be a single element, a beam member needs to be a single beam. All these things were nice when computer power is really limited. But if you want to do post-buckling analysis or plasticity, or you want to look into detailed stresses as well, you don't want to build several models for different problems. So with SDC Verifier, we took the other side. Okay, you have a model, let's see if we can use that model to do the code checks on. So whether you have a fine mesh or a single element for a full plate, we recognize this, we update the stresses in the right direction, and then we can do the code checking in that. Here the same principle, of course, but then for not maritime codes, but for the aviation codes. So we have the NECA tables, which was, by the way, for the non-aviation guys, this was done in '56. Yeah, the checks according to buckling is in '56, and I think outside aviation nobody knows that. Yeah, so I think that's a nice extra thing to see. We have member checks and joint checks according to offshore rules. If you need to have something like that, you definitely need software, so you can do that now in your Simcenter or VMAP model directly. I think this I'm going to skip. You can do very simple checks yourself with an easy to interpret a language, and you can password protect your own checks as well if you want. You can do also slightly more difficult ones, like for example a bolt check, where you set the different parameters like pre-stress. You can of course do a nonlinear calculation and applying the pre-stress in a model, but it's much easier if you just set that as a parameter, and then you can still use a completely linear model. So in short, SDC Verifier enables you to do code checking in your FEA program, VMAP or Simcenter 3D. We have a lot of standards available. You can customize these and password protect if you want. And what is also nice is the total calculation procedure is saved. So if you have a sequence, okay, I need to check this, this, and this, and this, immediately at the start of your project, you can already do all the code checks because you don't lose time in rebuilding a report later on. So instead of going, okay, let's first get yield okay, then buckling okay, then fatigue okay, then weld strength okay. In each of these times you have to go update your model, and then after that you can do the second check. Now you do all the checks all at once because you don't lose time in rebuilding your report. Yeah, so you get a better overview of all your problems. That's one thing. And so you can do with less updates because you have better insight. And the updates goes also much faster because everything is already set up. You update the stuff and all the calculations rerun automatically. So what are typically customers maybe? If you have high code checking demands, SDC Verifier is a good solution for you. High reporting demands is also a nice, and another nice thing is you can couple this with PLM and Teamcenter. You can not only update the reports, which is the simple step to do, but you can also use valuable info like weight of components, stresses, maximum stresses of components, utilization factors on fatigue or maximum fatigue life, and assign that to components so somebody else can see, okay, for a component I directly have the overview what has been done by this analysis and what are the results without opening anything and directly having the right info available. I want to end with a small example. I don't know how much time do I have? Another 5 minutes. So that's great. I can show you quickly, even for something which looks quite simple, like a crane. The advantage of this crane is that's 30 years old. So if you do fatigue analysis, you can really check if your results are okay, if they are realistic. While normally endurance is something you will figure out 10 years later, and then it's too late to make any changes. So what do? We have this crane. We set up first with the B model, just to get a quick overview. Okay, where do we need to put extra effort in making detailed results? Then you see everything which is of interest or where we think that the beam approach is invalid. For example, any connection, so connections all over here, but also here in the middle we apply, that looks completely like a beam, but the load is asymmetric. It is applied to one side with a rail on one side, and so you do expect local phenomenon there. So in the middle of the section we want to be sure that we catch all these details as well. And then side thing is also the trolley is of course completely modeled in plate models because, well, this does not look at a beam at all. So we first have all the trolley positions. So we have load positions. So they had the client defined 11 locations where you can pick or drop a load. And that is a good starting point, not only for the strength check, but also for fatigue analysis. So the first thing is, okay, we have 11 positions. We need to accelerate in 4 directions. I can move with my crane front or backwards, and with the trolley I can go to the left or to the right. So that gives up 4 combinations. So although it's 11 positions, 4 combinations, I already have 44 load cases only for operational conditions. Then the standards requires you to check the same working conditions, but then with wind. And wind is of course, you need from front wind, from the left and from the right, so that is 3 times again. So 3 times 44 load cases need to be added only for operational conditions with wind. Then we have storm calculations. We need to check that as well. Of course, then the crane is out of operation, but you need to have your trolley. You don't know where they can leave it everywhere. So we have extra 33 calculations on storms. We have a fatigue check. For fatigue check, we can use the lifting loads, but that is without, they are not the same as these maximum loaded working conditions, because you use more or less the average result. Instead of using the maximum container, you can use an average weight. So these are different from the maximum loaded operational conditions. And then you have, so the average load, and you also have the empty load, because you go, you pick something up, you move to a certain position, and then you put it down, and you go back empty. So we have 22 cases, load sets for fatigue, but then, so we have already with this simple stuff 231 load situations, which is even, we try to limit that. That is not even, this is the absolute minimum which is required. How do we do fatigue then? We have these 22 load sets, but we need to define the real situation. So we need to go from position 1 to position 5, from 2 to 7, and so on. So the client made a complete table where you have, okay, I go from rail track 1 till 4, and I need to move up to from 5 to 7. So I go from the red spots to the right, to the other one to the left. And they made an estimation on how often they went from one spot to the other. So there is here an estimation, okay, what is the real use of my crane? And how do you do that? So for if you take from the example, I take a small one, of course, because that is easier to see. So if you go from position 3 to position 5, we have 3 average load positions, so position 3, 4, and 5, and I go back from 5, 4, 3, I go back empty. So these 6 situations determine my maximum stresses and my minimum stresses, and from that I can calculate fatigue. And so I have for each of these situations the number of load sets and the stress variation in defined. So if we can compare the results, you can see here, this is the standard strength plot. So that's stress divided by the allowable stress, which looks like something which is where you're probably used to. You get a division over the model, which is varying gradually. But if you compare that for fatigue, you see something completely different. You see all these Weld situations popping up. And you can also, for example, if you only plot the welds, you can get a nicer overview directly. Okay, where do I expect fatigue problems? This is an example of this same crane where we found here a very high stress fatigue resistance problem, and we found a crack, not very big, but around 2-3 centimeters, and this is inside the crane, so you need to do inspection, and maybe I think they do this once a year. In general, they use this this equipment, and they do not inspect that so much. And from the outside, if you look at it, then you can find, hey, yeah, there is actually a fatigue problem. But this is completely not recognizable looking at its spots of dirt and debris which you have in general. So this is a very short overview of what you can do with SDC Verifier, how you can do code checks within your model, and how that can save you time, because you only need to build a single model, not a model for details and a general bigger model for within a code checking program. You can do both within the same environment. So the last slide is, if you want to report all this, we made basis of calculation, so the model set up, what are the loads, all these kind of things, 99 pages. I think out of these 99, at least 95 are automatically generated. A quick result only on the load group, so summary of the results, 44 pages, and a standard result report for every position, just a stress plot and a displacement plot, is 200 pages, and all of this is necessary in order to get approval. That is my presentation. I hope I clarified for you what we do, and I hope that you think, hey, that might be something for me. So if you want to contact me, or you contact me now, and I will wait here in the front, or you can contact me later by email or find us on the internet. That's it. Yeah? Mm-hmm. Mm-hmm. Okay, so the question is, how do you get the requirements of users? Well, the first and most, we started in 2010, and I already had since '98. I had quite some experience, and not only within my own consultancy, but I also teach. So I got to see the work of students, which is completely full of errors, figuring out what is wrong. I needed to have this reporting thing, model set up, see what is wrong, what are the loads. Hey, your boundary conditions are slightly are not completely correct. You made a typo in a specific individual load. All these kind of things require you to set up in a separate way. So calculating according to the method of standards makes also checking of what is okay and what is not okay much easier. Because if you have a lot of loads together, you check maybe the 3 biggest influences, and then if the number, the total sum of forces matches more or less your hand calculation, you think, well, it's probably okay. In this way, you can do that even for the small loads. You can say, okay, this is exactly what I need or not. Yes, there's another question.
What I see is very nice work in calculating up to the standards. Typically, you do that so that you get an accreditation by some kind of government agency or something. Is the documentation that you make up actually accepted by these agencies as part of the process?
Yeah, that is one part why you need this extensive reporting. And the nice thing is that all the formulas, all the approaches, everything which is in that standard is added to the report. So it's completely open. That is why it is accepted by government agencies and also, for example, DMV or Lloyd's. Yeah, and you can also send out an empty report with all your loads, with your approach for approval. Say, look, this is going to be your approach. Are you agree on this? So before you do any calculation, any results, you already send. Yes, and you can, that is a nice extra advantage of having something like this. Okay. Okay. Thanks.